Maybe. Probably. Honestly, they trying to put that stuff together all the time. Alright, so let's talk about this again. We've got here. Oh wait, this was supposed to be dotted lines. Actually,
Americium.
this is our transition metals.
Tennessee.
Americium.
Plutonium.
We're gonna use them a little bit. We're gonna talk about them a little bit.
How do you pronounce that one? 70 at the bottom. 70 at the bottom.
Alright, so I know I went over this yesterday, but I feel like I may have glossed over too quickly because I had people asking me, how do I tell what metal I am? And they were asking about transition metals. So these are all called transition metals. We only skip them when it comes to counting the number of valence electrons because they have a strange amount of valence electrons. Typically, they can be one or two, but they don't actually react the way that the ones that have one or two solid ones. So it's kind of a funky situation. All right. So, and then everything from here, let's see here, we got boron here, stair step down. All of these are metals again. All of these are non-metals. And if it touches the line, unless it's aluminum, these are metalloids. And I probably had something about like the rows equal number of electron orbitals, how many rows it is, or the columns. I don't remember where I wrote this here.
Yeah, you wrote it on the side.
Columns equals number of valence electrons. So I probably did like a scallop dagger. Do you need somebody? What? Oh, I can do that, I guess. No. Alright, so anything else that I'm missing?
This far side is alkali metals, right?
Alkali.
Alkali.
Yes. So this whole section, when it comes to making your periodic squares and color coding, because that's important. Alkali metals, other metals, metalloids, non-metals. Okay, so we can put other metals on here if you like. And these are all alkali metals. Now there are two different types of alkali metals, but just for the purpose of this class, we're going to just call them all alkali metals. And I don't have any.
KIALI. ALKIALI.
So alkali. Alright. Now these are objective 1 and objective 2 of periodic table. Question?
There's something. I don't remember.
It's alkali metals and alkali earth metals.
But something happens when alkali metals mix with something else.
Yeah, non-metals. They form
Hydrogen, alkali, and natural gases add progressively when you mix them.
And also this column is all noble gases, so they're
Hydrogen and alkali act progressively.
so they create acids. Probably.
Yeah.
It's like hydrochloric acid.
I'm just trying to piece together pieces of it.
All right, so periodic table, that was part 1. Okay, this should all be reviewed. Again, I do expect you guys to write it down, so if you are not writing it down, make sure you do so. This will help you for your periodic table focus area. That was objective 1 and objective 2. 1 and 2. All right, now objective 3 is the meat of the matter, is the most difficult part of the matter. And I think I'm going to draw it in another color just to distinguish the difference. Okay, so objective 3 is what we're going to be talking about now. The very first thing objective 3 talks about is it talks about further out is the atomic radius. Remind me what electrons are, what charge they are.
Negative.
Negative. And what's the charge of the nucleus?
Neutral.
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 Positive.
Positive, because it has the protons in there too, right? All right, so what's happening is the electrons are all being pulled toward the center. It's just like two opposite magnets. When you put them near each other, especially if they're strong, they pop together, right? So the electrons are being pulled toward the center. And the more electrons there are on the outside, the harder they pull. Okay, but we're going to talk about that in a second. So as you move down the periodic table, what happens to the number of orbitals in general? There are more, right? So what does that mean for the atomic radius? As you move down the periodic table, what's happening to atomic radius? Yeah, it's getting larger, all right? So we're just going to say atomic radius, okay. And I like to do it visually. If you need to write the words getting larger or whatever, that's fine. But honestly, like, I like to make it like visual. This is how I work. All right, so atomic radius. Atomic radius. It's getting larger. Up and down. That makes a lot of sense.
Is it in that triangle kind of thing?
Yeah, so like big at the bottom, little at the top. As you go down, atomic radius increases. It's just like when you have this sort of a symbol on your volume, you know, toward the big side it gets larger, toward the little side it gets smaller.
Like as it goes up, it gets smaller or larger?
As it goes up. So as you, atomic radius gets larger as you go down the periodic table. Just naturally, because there are more rings. I think you understand that already. Because more down, if you're counting down, you're getting more rings. It's going to get larger. Just have to. But this way is the weird way. Because as you're moving across the periodic table this way, what's happening to the number of electrons on the very outside?
Bigger.
They're multiplying.
There's getting more of them. I'm hearing it's getting smaller, but I think you're skipping ahead. So we got to talk about this. I think you are. She's like, I think you are. So as you're moving across one single row, so let's take one single row. As you're moving across one single row, it's increasing the number of valence electrons. That means that it's increasing the pull from the outer ring in. All right, so as you move across here, it actually gets smaller in one ring. I told you you're hot dog ahead. All right, so it actually gets smaller with, I guess I have to not. It actually gets smaller as you're moving across the ring. Or across the thing. Because more electronegativity on the outside pulls more in. Okay? It's pulling harder. So more valence electrons, let's do this. More valence electrons equals the outer edge, the outer ring is pulling tighter. Let's put outer ring. It pulls in more. Okay. Yes.
You're saying there's an electromagnetic pole, and I get that electro is meaning electric, but what's the difference between electromagnetic and magnetic?
It's actually electronegative pole, because electromagnetic is the same as magnetic. Electromagnetic just simply means a magnet that is using an electric current to be magnetic.
Yeah, but so something could be just magnetic. So But in this sense, is it electric? Or is it just
No,
magnetic?
it's not electric in the sense of electricity, but electricity is the movement of electrons, and it has to do with electrons.
Okay.
So it's not actually electromagnetic, it's electronegative. So it has to do with it's not a magnetic pole, it has to do with the interactions between the two positive and negative. Alright, so let me make sure I'm going wrong. Alright, so the size of the radius increases. Now, there are these crazy things called ions. Yes. Sorry, it decreases.
I just want to make sure that I'm reading this right. This means that francium is the largest.
Francium would be the largest in terms of radius. Francium would be the largest in terms of radius, yes. So when you, just like I have here, atomic radius. As you go across, it gets smaller because there's more stuff to pull. Okay, no, you're fine. Well, are you going this way or so it has to get larger as it goes down. Has to get larger as it goes down because there are more rings. Okay. Let's talk about ionization. Okay. Does anybody know? Has anybody heard of an ion before? Okay. Could anybody explain what an ion maybe happens to be? All right. This is my favorite way to describe ions. Valence electrons can be like change. If you don't have that much of it, isn't it easier to like put it in the can of the homeless guy sitting outside the liquor store or whatever?
Oh, you mean literal like money change?
Yes, like money change. Like
I thought you meant like
so
changes and
you've
something
got-
is changing.
Oh, I got you. No. So like you're walking out of the liquor store, you realize you have 12 cents. You're like, well, this is not even close to $1. I don't need it. You know? But if you have 95 cents, doesn't that seem like something you're gonna hold on to a little tighter? It just feels like it's closer to $1, right? Alright, so I like to think of ionization like that. If an electron, and so we're looking for again 8, is that magical number? Because 8 fit in a ring. If you're looking at something that has only one electron, it's very likely to just toss it away. Because then it has whole bills. It has whole full electron rings, electron orbitals. But if you're looking at something like chlorine, it's almost there. How many electrons does it need to have a full ring? Just one, right? So it's going to try to snag that electron that somebody else is throwing away. Exactly. So if it's closer to this, if it's closer to having a full ring, it's going to throw it away. Now, an ion simply means something that has a charge. Okay, ion equals a charged atom. Charged atom. So what that means is, say we give calcium an extra electron because it had 95 cents and it found a nickel on the ground. Then it's chlorine. I don't know why I'm obsessed with calcium today. Maybe I should take calcium, right? So it got an electron. It picked it up from, I don't know, sodium that dropped it. So it no longer has an even amount of protons and electrons. You should be writing this part down. I know it's just a tiny thing. So it no longer has the same amount of protons and electrons. So it has an extra electron. So what charge might it have at this point? A negative charge, right? Simple. Okay. Now say you have sodium over here. And it got rid of an electron. It has more more protons than it has electrons. What's sodium's charge?
Positive.
Positive. Alright, so those are just ions.
NA is
Sodium.
oh, that's
35.
so then that little plus is an ion.
It's a charge. Anything that has a plus or minus next to it is charged. Okay, has a charge. Okay. So ionization energy is the amount of energy it takes to become an ion. The amount of energy it takes to become an ion. So this guy down here, now this is not in a capitalist society, let's just put that aside for a second. Okay, this guy down here, Francis, he's got a valence electron floating out there far, far, far away from him, right in the center. He's got tons and tons of other electrons. He's got 7 rings of electrons, 7 full rings of electrons. Well, no, sorry, 6 full rings of electrons, and 1 floating ring. He's a billionaire when it comes to electrons. You think that might be a little easier to get rid of that last electron than it is for lithium that only has 3 electrons?
Yeah.
Yeah, he's like, okay, I've got $2, but I also have this nickel. I'm gonna hold on to the nickel just in case something costs too much. Okay, that's how I just think that money makes things a little bit more accessible to think about this.
Yeah.
So as you move down the periodic table, ionization energy increases. Jordan, put your phone away, please. All right. Or sorry, it decreases. So I'm gonna draw this backwards thing here. So as you move down the periodic table, ionization energy decreases. Yes. Electronegativity. It increases going down because there's more electrons. I think that's what they're testing on.
I don't have enough room for all these lines.
I just don't want to go overboard. I'm looking at the questions in this because I just don't want to like overload you guys with information that's actually not going to be tested. All right, and then as electrons become more, and electronegativity increases. Okay, so as there's more electrons, electronegativity increases. So actually, if you look at atomic radius here, I guess I can't say it that way. So as you have more electrons, electronegativity increases. So I'm just going to write that rather than drawing another thing on here. More electrons equals higher electronegativity. So we're gonna have more practice on this stuff. But for now, I want to stop talking and allow you guys to start working on a little bit more of the periodic squares. Now, as people get finished with both of their periodic squares, I will allow them to choose their third one at this point. If you're choosing first, you're going to end up choosing one of these anthonides and lanthanides and actinides. I can't remember what they're called. Yeah, lanthanides and actinides. You're going to choose one of those, and those can be any color. I do not care what you color your text. Okay. So the first, potentially 15 people who finish will be able to choose their own. Now, this is the last day we're actually gonna be working on this in class, because Monday, we need to start putting it up on here. Well, I'm gonna probably do it after school. Yes, that's a good idea. So, if you could open up your checkpoint, make sure you understand the requirements, make sure you understand, which color coding you should be looking at, and then start looking for your periodic square.
I don't remember. You know what?
Markers. It's like,
I didn't charge that last night.
so I like eating everything. Also, my grandparents.
Can I come choose
So
your
my
Lance
mom-
and I or back and I?
So for her 13th birthday, she asked for
You
like
got lucky.
a salmon. Something crazy that makes super fancy that no 13-year-olds should know.